So this is now, we are recording. This is Thursday of week 15. This is coming to the end of the semester. And today is a reviewish day where I am answering questions that people have, as will be next time. And someone said question on 35, which is this the right one? This is question 35. Oh, I don't want to keep doing that. Yes, how do I see you? Chat. So yes, okay. So the question is, a recent flyer was interested in the relationship between dollars spent on flying and the distance flown. This is two quantitative variables. Two quantitative variables is what we would use a scatter plot and correlation and regression for. She sampled 20 frequent flyers of a certain airline. She collected the number of miles flown in the previous year and the total amount of money the flyer spent. A regression line of distance flown, which is your y-axis, on money spent. So spent is on your x-axis and distance flown is on your y-axis, was fit to the data. And the intercept and slope were calculated to be 24,000 and the slope was 10. So the line would look something like this. All right, it's a very small slope compared to a value of 24,000. I don't really have a full scale here, but 24,000 on the y-axis. So I have an upward slope of 10. And you can see my y value is distance flown and my x value is money spent. Because if you think about it intuitively, the more money you spend, the greater the distance. That should be the causal relationship, should there be one. One of the randomly sampled frequent flyer was found to have spent 2,500. That's on the x-axis, 2,500. And flown 41,000 miles. So that point is most probably not on the line because most points don't end up on the line. But we see that at a money spent of 2,500 as the x value, there is the corresponding y value of 41,000. And the question is, what is the residual? Well, the residual is by definition observed minus predicted. So the residual is equal to 41,000 minus the predicted. So the only question is, what is the predicted? Well, what is the equation of my regression line? Since we have the slope and we have the y-intercept, if I put in a y equals mx plus b form, what do I get for the slope? Sorry, what do I get for the equation of the regression line? What is it equal to? What is the equation of a line if you know the slope and the y-intercept? Anyone? All right, well, this is has been a good talk. Yes, y equals mx plus b. M is 10, b is 24,000. So the equation of the best fit line is that. So if I want to know what the predicted is, I just plug in my x value, 10 times 25, 10 times 2,500 plus 24,000 gives me a predicted value of 49,000. So my residual would be my actual value of 41,000 minus my predicted value of 49,000, which gives me a residual of negative 8,000. Now that I've done the math, what is wrong with my picture? My picture was generic, but now that I've done the math, what is wrong with my picture? The slope was 10. The slope was 10. So there's something wrong with my picture. Now that I've completed the problem, there's I mean, it doesn't change my math. My math is still negative 8,000. That's still correct. It's just my picture is wrong. What is wrong with my picture? No, It's a positive slope, so it's an upward trend. The more money you spend, the further the distance. That makes sense. The answer is that I picked my point 41,000 above the best fit line. I have 41,000 up here, but the prediction is 49,000, which means my actual point should be underneath the line. So that observed minus predicted is a negative number. Negative residuals are when you're beneath the line. Positive residuals are when you're above the line. So now that I've actually calculated my residual and I got a negative number, my dot should have been beneath the line. Doesn't change what I did. The angle, I don't know what the angle is. It's the tangent inverse of 10 officially. It's just a sketch. It's not an accurate picture. Anyway, does that make sense for that question? He who asked, was it Anthony? Who was it who asked? Andrew. Does that make sense? Sorry, all those A words.
You can't have any piece of the orange, can you?
Or the sandwich, which looks really good. The slope is 10, not 10x. 10x is the slope times a variable, but the slope is just 10. All right. So I hope that made sense. I'm going to stop sharing and pause my recording until the next question is out. So we have another question on the table. It is question number 30. So let's go up to 30. Question view. Frequent food questionnaires. Am I sharing my screen? I don't think I hit that. Okay. Hold on. People texted a few things. Let me see what they said. You should put some tagine on that cucumber. What the hell is tagine? I don't know. Is that on my food plan? I don't even know if that's on my food plan. I'd have to ask. And then there's question 25, chapter 25, question 4. Oh, it's chili powder. Tagine. I'm going to write that down because I don't speak that language. Tagine. All right. So sharing my screen, we have the following question, question 30. Frequent food questionnaires, FFQ, are a simple way to obtain information on the foods individuals consume by asking them questions about typical amounts of food consumed in a day, a week, or a month. A more accurate picture is obtained by obtaining a detailed food diary, DR, for several days that are randomly chosen over a certain time period. The data obtained from a frequent food questionnaire can be compared with the food diary to assess the validity of the questionnaire. The data below are for 7 individuals, 1, 2, 3, 4, 5, 6, 7, okay, who participated in such a study on alcohol consumption. They just want to know the correlation. Well, this is a calculator problem. You don't do this by hand. You go to your calculator, you go to stat, you go to edit, you clear the first and second columns, you do 8.26, you do 0.83, you do 20.13, you do 11.16, you do 7.18, leave me alone, oh my God, you do 1.76 and 22.66, and then you do 1.68, you do 0, you do 15.1, you do 7.49, 12.84, 0, and 25.06. Then you go back to stat and you go to calc, you go to two var stats and you say, I want to calculate, oh, it wasn't that one. Okay, stat, calc, let's go to RenReg, go through it, and we get a correlation of 0.889 or 0.89. But answer is 0.89. That took all of what, a minute, give or take. If I did this by hand, even knowing the formula, it would still take me probably a solid 4 or 5 minutes to go through all the math. Know what your calculator can accomplish for you so that you don't have to do it. Does that make sense for that one? Oh, it's pronounced tahim. I'm going to resume recording now because we have another question. This one is on chapter 25, the practice quiz, it sounds like. So here I am giving away an answer to one of your practice quiz questions. Okay, let me share the screen here. We going to join this Zoom link for the final? I would think so. That's where I'll be. And who will want to be here with me? That's all I got to say. Ryan, was it number 4? Was this the one? What does it cover again? Everything. If we did it, you need to know it. Ryan, is this the right question? Hello, where's Ryan? Hello. Is this the right? Am I sharing? Do you guys see what I'm sharing? Okay. A study was conducted to assess the effect of some drug on the treatment of patients with agoraphobia and panic disorder. The 3 treatment groups were control, that's group number 1, a low dose of particularly 1.5 milligrams per kilogram of body weight, and a high dose of 3 milligrams per kilogram of body weight. There were 70 patients, with 30 assigned at random to the control group, 20 to the low dose treatment group, and 20 to the high dose treatment group. At the end of 24 weeks of treatment, patients were classified as responders or non-responders to treatment. So there's 3 groups: control, low dose, high dose, and either they were a responder, or no, they were not a responder. So we have 6 cells of data: 6, 24, 9, 11, 9, and 11. The table gives the observed counts as well as the expected counts. Let's just confirm the 10.29 is correct. How would I get the expected count for this cell? What would I do to get the expected count for that cell? Who remembers? You take the total for the row, which is 30, the total for the column, which is 24, you multiply them, and then you divide by the overall total, which is 70. I just did it on my calculator. I got 10.28571429, which does in fact round to 10.29. So I'll assume that the other values are correct as well. Suppose we wish to test the null hypothesis that the probability of being a responder is the same for all groups at the 5% significance level. In other words, that it's independent, that one does not depend upon the other. It's the same. What is the value of the chi-squared statistic? Well, what's the formula for the value of the chi-squared statistic? Anyone, what is the formula for the value of the chi-squared statistic? And by the way, if you can see this is my survey. In our class, I only have 26 of 46 who have taken it, as opposed to a significantly higher percentage here and a significantly higher percentage here. So I would like everyone, before class is over, to go to the website and do the evaluation. I'd love for this number to increase. But for now, what was it again? Sigma times well, first of all, sigma's not a number. You're not multiplying sigma by anything. Sigma is telling you to add stuff.
When he's getting off work today and he said 8, he's like, why, do you miss me already? I was like, yeah, of course. But I meant it in a sarcastic way because we always do that.
What just happened? Wendy, you talking to me?
No.
Uh-oh. So she's not focused on the class. Uh-oh. It's not O minus, it is O minus E squared divided by E, but it's not sigma times that. The sigma is telling you to add them all. Do it for the first one. Do it for the second one, the third one, the fourth one, the fifth one, the sixth one, and then add them all together. So let's see if I can do it in my head and get a rough estimate. 6 minus about 10 is 4. 4 squared is 16. 16 over 10 is about 1.6. So the first one's about 1.6. Already this one's out. 24 minus 20 is 4. 4 squared is 16. 16 over 20 is a little less than 1. Let's say it's about, I don't know, 0.8. So let's say now we're about 2.4. 9 minus 7 is 2. 2 squared is 4. 4 over 7 is about 0.5. 7. 11 minus 2, 2 squared is 4. 4 over 13 is about a third, so about 0.3. 9 minus 7 is 2. 2 squared is 4. 4 over 7 is about another 0.7. And then 11 minus 13 is 2. 4. 4 over 13 is about 0.3 again. So it looks like it should be somewhere in the vicinity of 1.6 plus 2.4, 3.1, 3.4, 3.7. I get about 4.4 as my answer. So both of these numbers are close enough to 4.4 that I would probably say, yeah, I want to do it a little more specifically, but I'm going to go with that one. Let's see if I'm right. Solution is 4.76. That's what I'm talking about. Yeah. Sorry. Just, you gotta, that's what I'm talking about. What can I say? So, yes, there's the link, www.csunday.edu/SEF for the 20 people who have still not taken it. So I would love it if you would do so. Anyway, does that make sense for this one? I don't recommend doing it like I did, only because it's a test. Why? Even if I could do it this way, if it's a test, I would do it with as much accuracy as possible. But at the end of the day, all this nonsense here, didn't need any of it. Didn't need any of it. I just kind of saw a two-way table, saw the observed and the expected, and said calculate the chi-squared. Well, I have the formula for the chi-squared. Plug it in, get my answer, and done. So does that make sense? Now, whether or not we reject the null hypothesis, let's follow it up. Even though this wasn't part of the question, let's follow it up. Do I reject the null hypothesis or do I not reject the null hypothesis in this scenario? So in order to determine that, I need to know how many degrees of freedom I have. So how many degrees of freedom do I have? How many degrees of freedom do I have? Well, the formula for degrees of freedom is rho minus 1 times column minus 1. How many rows of data are there? 3 rows of data. How many columns of data are there? 2 columns of data. So 3 rows, 3 minus 1 is 2. 2 columns, 2 minus 1 is 1. So the answer is there's 2 degrees of freedom. Anthony, do you agree with that? You don't know why? Well, how many rows of data are there? There's 3 rows of data, correct? I was being dumb. Okay, well, that does happen. I was dumb once. That was in 1987, I think. So, but I learned from my mistake. And now I'm just dumb privately so that nobody can see me being dumb. Well, that's not true. I'm pretty much dumb all the time. So now that I know how many degrees of freedom I have, now what we're going to do is we are going to load up a chi-square table. And you don't count the total columns of rows, right? The formula is rows minus 1, columns minus 1. That is the formula for the degrees of freedom for a two-way table situation. And if it's greater than 0.05, it's the null hypothesis is not rejected. It's not accepted. It's not rejected. So our chi-square statistic was what again? 4.67, 4.76. 2 degrees of freedom, 4.76 is between these two numbers, which is somewhere between a 0.05 and 0.10, probably much closer to 4.6. And therefore, we would not reject the null hypothesis because the p-value is greater than 5%. And therefore, there is not enough evidence to conclude that they're not independent. We can't say they are independent. There's just not enough evidence to prove or to conclude that they're not independent. Your standard conclusions based upon your p-value. compared to 5%. So here we are resuming our recording for our next question. This is number 16 on the practice. So let me share my screen again. And we're going to 16 on the practice. This one on here, right? Question, no, not solution, question. This one? I just want to make sure I'm in the right place. Is this the question you have? $16, please, in the practice review. Are we not on? Oh, on the practice review. Okay, sorry. Which practice review? There were 3 of them. Which one do you mean? The first one, the second one, or the third one? The first one, okay. Okay. According to the College Board, SAT mathematics scores from the 2014 school year for high school students in the United States were normally distributed. Oh, I love normal. A normal curve, normal distributed, with a mean of 513 and a deviation of 120. And even before I read further into the question, I've already made my normal curve. I've put in 513 at the center, and I've indicated that the standard deviation is 120. Use a standard normal table such as this one to determine the probability that a randomly chosen high school student who took the SAT in 2014 will have a mathematics score between 400 and 750. Well, 400 is about there, and 750 is about there. So we are looking for the probability of being between 400 and 750, correct? Right, we want to know what's the likelihood of being in the shaded region. Do we agree?
Yes.
Okay, I love the confirmation from one person. So let's go to this one. And this one, table values represent cumulative area under curve to the left. So if I want to use this table, I must compute 2 values. To the left of 750, to the left of 400, and then I would subtract them off. So to the left of 750, well, notice that these are z-scores, and 750 is my raw data. So let's compute 750 to its z-score. What is the z-score, or how do I compute the z-score for 750? What do I do to compute its z-score? How do I compute the z-score for 750? Uh-oh, if you don't know how to compute a z-score, we got big problems. How do you compute a z-score? X minus mu over the standard deviation. So what is the X? What is the mu? And what is the standard deviation? Your numbers are different. We'll use my numbers because that's what we have in front of us. What is the mu and what is the standard deviation?
Standard deviation is 120.
Standard deviation is 120. They literally say that. And what is the mu? No, yeah, I'm sorry, 513, right? Mu is 513. So how do I compute the z-score for my score of 750? How do I compute my z-score for my score of 750? I take my data point, which is 750, subtract mu, subtract 513, divide by sigma, divide by 120, and I get 1.975. If I do the same thing for my score of 400, if I want my z-score for 400, I do 400 minus 513 over 120. And I get negative 0.942. So underneath my raw data, I computed my z-scores. 400 corresponds to negative 0.942, 513 corresponds to 0, and 750 corresponds to 1.975. So now I can go back to this one. What is the probability of being less than 1.975? Well, let's find 1.975. Here's 1.90. 1.900, 1.901, 1.902, 1.903, 1.904, 1.905, 1.906, 1.907. Here's 1.908. We want 1.90975. So we want the number right in between them. It's a pretty good estimate. So let's take 0.97558 plus 0.97615 and divide by 2. So we get 0.975865 approximately as the probability of being less than 750. The same thing with the other one, which is negative 0.942. I go to negative 0.9091929394. It's between these two, and it's much closer to this one, so I'll just use that one. 0.17361. And when I subtract, I get about an 80.2% chance. 80.2% chance. Okay, 80.3. So we're pretty close. Did that make sense for that one? So another question on the table is question number 24. So, no, I don't think I'm sharing. So hold on, share 30 minutes equals 0.3. Sorry, what was that? Oh, it's the question. The average time taken for your internet service provider to remotely resolve a trouble ticket has a normal distribution. Oh, normal distribution. So let's make my normal curve. I want to visualize what's going on here. With a mean of 4.3 hours, so 4.3 is in the center, and a deviation of 3.1 hours. So we have my normal curve, mean 4.3, deviation 3.1. What percentage of the tickets are resolved in less than half an hour? A half an hour is 0.5 hours, correct? It's half an hour, so it's 0.5 hours. So we just want to know the probability of being less than 0.5. And we do it in exactly the same way. I'll use my calculator for this one for a more exact answer. So distribution, normal CDF, negative infinity to 0.5, where the mean is 4.3, the deviation is 3.1, and we get an answer of 11.0%, 0.110136 actually. If you really want to be a stickler for accuracy, we round the 5 to a 6. Another question has been asked. This one's number 20. Let's share the screen again, and let's find number 20. I'm going to cover. They always do the answer by accident. I don't know why they do that. All right. Now the purport. This is the same thing. You tell me how to do this one. Oops. Oop. Ooga booga. Your nephew thinks he's a comedian. Well, if he was really a comedian, he would know that Ooga Booga is not funny. So now if I said it, that would be funny. See, it's all in the delivery. Anyways, the proportion of observations from a standard normal distribution take values between 1 and 2 is about what? What is the proportion of observations from a standard normal that's between 1 and 2? Go directly to the calculator. Do not pass go, do not collect $200. We want to be lower 1, upper 2, mean 0, sigma 1. We get an answer of 13.6%, 0.136. Not 135, 136, but you know, you give them a little leeway. They're under a lot of stress, these people. So, you know, if they're off by 0.1. And we're back. Another question. This is question number 29. So let's load it up. Here we are. Question 29. Are higher than average sea surface temperatures associated with a greater than average number of hurricanes each year? In a 2010 study, the average global sea surface temperature anomaly was recorded, along with the number of Atlantic hurricanes above or below the average for that year. The response variable is. The response variable, well, the answer is already there. I don't know why it goes to solution automatically. It really shouldn't. It's really annoying. I will have to give them a talking to. But the response variable is, right, there's two ones. There's the explanatory variable and there's the response variable. The explanatory variable explains the response. So which one is causing the other? Not causing, because it's not always a causation, but you know, which one do we intuitively believe to be the one that explains the other one? Does the number of hurricanes explain the average temperature, or does the average temperature explain the number of hurricanes? Well, you can easily measure the average temperature, and as a result, you can use that to ideally predict how many hurricanes there's going to be. So the response would be the number of hurricanes. The explanatory variable would be the global sea surface temperature. Sounds like a podcast, Lamau. What sounds like a podcast? Do I sound like a podcast? And coming soon to a theater near you. No, that's not a cow. That's like a trailer. When you start recording, I thought I was recording. I'm going to pause recording now. So here I am resuming my recording. And that is true, Leah. It is true. So let's go to question number 18. And okay, what's that? That's one. And it's let the podcast continue. So here we are, and answer question number 18. The question reads as follows. How do I, oh, there we go. Use table A to find the value Z of a standard normal variable that satisfies each of the given conditions. Use the value of Z from table A that comes closest to satisfying the condition. In each case, catch a standard normal curve with your value of Z marked on the axis. Find the point Z with, oh, here are the answers again. God damn it. Find the point Z with 66% of the observations falling below it. So 66% of the observations. So we go to, so we can have a probability of 0.66 to the left. How do I know it's to the left? Because this thing here tells me it's to the left. Here's my Z and it's to the left. So I'm looking for 0.66, 66%. 0.66 is between these two numbers. This is 0.09 away. This is 0.0009 away. And this is 0.0028 away. So this one is closer. So we're going to use 0.41 as my Z. And that was in fact 0.41. Then it says find the point Z with 16% of the observations falling above it. Well, if 16% fall above it, then 84% fall beneath it. So we try to find 84%, which is, here's 0.8389, And the next one is 0.8413. This is 0.0011 away. This is 0.0013 away. So we're going to use this one, which is 0.99. Boom, 0.99. So let's resume. And here we go. Number 22. So I have to, I'm a crier. What can I say? I cry during movies and stuff. I don't cry in real life. Like nothing actually affects me in real life. But like when I see things in movies, I cry. I have to admit it. Like when they killed Jaws at the end, I cried. That was sad. All right. So question number 22 someone has. So let's take a look. So suppose you received a score of 91 out of 100 on exam 1. Way to go. The mean was 79 and the standard deviation was 8. What, oh, goddamn solutions. What score do you need on exam 2 to do equally well if in this case the mean is 60 and the standard deviation is 12? Well, what is it about doing equally well? Your z-scores are the same because your z-score tells you how far away from the average you were in terms of standard deviation. So in the first exam, I got a 91. Mean was 79. 91 minus 79 is 12. 12 over 8 is 1.5. So my z-score is 1.5. So 1.5 equals something minus 60 over 12. 1.5 times 12 is 18 plus 60. The answer is 78. So the answer is 78. Not as high as a 91, but the average was a lot lower. So you don't have to score as well to do as good relative to your peers. So there was that one. Sounds like a question for Crunch It. Actually, no, it was not a question for Crunch It. Crunch It would not be able to do that one. That one requires you to know what it is that they're asking for and then how to go about finding the solution. See, the thing about Crunch It is if you plug in data, Crunch It will pop out an answer for you, and that's fantastic. That's fantastic. But sometimes you have to know what to do, and Crunch It doesn't tell you. Crunch It's good at crunching data, but it's not good at knowing the strategy for solving the problem. You have to recognize that it's the z-scores that are the key, that to do equally well on a test, your z-score has to match. So you calculate the first z-score because you have all the information you need, and then you use that to find the data for the second one. And then you can count in your head. It's just you might not be able to count as high as how fast, but you know, if you can't get to 3, then we got problems. But everyone should be able to get to at least 3 in their head. See, I did it very quickly. Actually, I saw a great meme the other day. Someone's on a job interview, and I'm going to stop recording because there's no need. Well, people watching my meme. So someone's on a job interview, and the person's reading the resume and says it says here that you're very fast at math. And the person's like, yeah, I'm very fast at math. The guy goes, okay, what is 723 times 685? And the guy says 17. And he goes, that's not correct. He goes, yeah, but it was fast. So you can be fast. It's just being fast and accurate that you're going for, not just fast. That's all I'm saying. We can all be fast. Anyway, now that I have that, I can stop recording. Resume, and here we have another question. We are now doing number 7. So number 7. All right. So, oh, go wait, solutions. No solutions. Why does it do that? All right. Suppose Ted is creating a football team in a video game that features many NFL players. He decides to identify players who are outliers in a few statistics he has chosen. Currently, he's looking at wide receivers. The game includes the top 250 receivers in 2016 by number of receptions, which is a pretty good metric. Ted, however, is more interested in receiving yards, and the table shows the 5-number summary of the available players in the game. Minimum 70, maximum 1,448, huge. Third quartile, 6, okay, fine. And we also have the mean, and we have the standard deviation. Ted first calculates the interquartile range IQR, which is 673 minus 210, which is 463. Next, to determine suspected outliers, he calculates Q1 minus 1.5 IQR and Q3 plus 1.5 IQR. And someone texted something. Just the last part. Fine, just the last part. Jeez, okay. So those are the Q1 minus the 1.5 IQR and the Q3 plus 1.5 IQR. Ted identified the top receivers available in the game by receiving yards. So which are the anything less than this number or more than this number would be a suspected outlier. So anything more than 1367, that would be T.Y. Hilton and Julio Jones. That's the last part. I guess I just did that one already. All right, anyone past this number to the left or past this number to the right would fall under the category of suspected outlier. So what's past negative 44.5? Nobody, because the minimum was 70. And what's past 1367.5? Just T.Y. Hilton and Julio Jones.